Welcome to week 10, and this week we are going to lay some theoretical foundations for what we're going to cover next, which is Markov chain Monte Carlo methods. So Markov chain Monte Carlo methods is going to be our next topic. A key task in statistics is to estimate parameters, which we usually denote by theta, of statistical models based on some observed data, x. Here I used a bold x to denote a vector of length n if we have n independent samples from the distribution. So Markov chain Monte Carlo, which is MCMC, provides a flexible approach to Bayesian model parameter estimation. Before going into the details of the algorithms, it might be a good idea to start with a review of Bayesian theory as well as discrete time Markov chains. So let's begin with some Bayesian inference and Bayes statistics. If you have taken 410, this might be something that has been covered at the end of the semester. If you have taken a Bayesian course, this will be nothing new to you. So let's consider the following case where we collect a sample X. There are a total of n samples from a probability distribution that depends on an unknown parameter theta. Here, theta can be a scalar, so a simple number such as the Bernoulli probability of success, or it can be a vector. So theta can be, say, the normal mean and the variance together, or something else like your regression model parameters. So our unknown parameter is theta and our data is x. Then the likelihood function of theta, which is the joint probability density of the n observations as a function of theta, is given by this formula over here. So we usually denote it by L theta, or L theta semicolon x, meaning that this is the likelihood function of theta given these data. And that's simply the joint distribution of our observed data given a particular value of theta. When the x1s all the way up to xn's are independent samples, or ID samples, then in this case, the likelihood reduces to the product from I to n of fxi given theta. So in frequentist inference, theta is treated as a fixed but unknown value. So the unknown parameter is a fixed number that we are trying to estimate. So how can we estimate that? A common way to estimate the unknown parameter is to find the value of theta that maximizes the likelihood function. In other words, what is the value of the unknown parameter that will make it most likely for me to observe this particular data set? So this is known as maximum likelihood estimation. And we will come back to this in a couple of weeks when we talk about optimization and talk about the expectation maximization algorithm. So in general, the maximum likelihood estimator of theta, which is an estimator of theta, is given by the argmax of the likelihood function for theta. In other words, theta hat is equal to whichever theta value that maximizes the likelihood. Alternatively, in Bayesian inference, the parameter theta is actually viewed as a random variable. This is in contrast to frequentist statistics where the unknown parameter theta is assumed to be a constant. In Bayesian parameter estimation, we first use theory or prior knowledge to specify a prior distribution of theta before data collection. So because theta is viewed as a random variable, we first use our prior knowledge to specify a prior, which we denote by f theta. So that's the distribution of theta based on our prior knowledge. And then when data is collected, they can be used to update the prior beliefs. And how do we do the updating? So assuming that theta is also random will allow us to specify a joint distribution of the data and the unknown parameter theta, because both of them are random variables. In this case, the joint distribution of our data x and unknown parameter theta is given by the marginal distribution or the prior distribution of theta times the conditional distribution of x given theta. So you can see that this joint distribution is equal to the prior times the likelihood. So how exactly do we update prior belief about theta based on our observed data? In Bayesian inference, we look at the posterior distribution of theta. In other words, the conditional distribution of theta given the observed data. So by the Bayes rule, we know that the probability that A given a conditioning on B is equal to the joint probability of A and B divided by the marginal probability of B. So we can use this to find out what is the conditional distribution of theta given our observed data. So f theta of x, which is the density of theta conditioning on x, is given by their joint distribution divided by the marginal distribution of x. The numerator is what we had on the last page, which is the joint distribution of x and theta. And that's the product of the prior and the likelihood. The denominator is the marginal distribution of x. And in general, we can obtain it by integrating out theta from the joint distribution as follows. An important point to remember in Bayesian inference is that once we observe the data, the only random term left is the parameter theta. Therefore, the denominator in the posterior distribution, which is fx, can actually be thought of as a normalizing constant. So we can call it c, because once we observe the data are now constants and no longer random. In this case, we can rewrite the posterior distribution as the likelihood times the prior divided by the constant c. And another way to put it is that the posterior distribution is proportional to the product of the likelihood and the prior. So this symbol in LaTeX is called prop2, denotes proportional to. And because the posterior is equal to this thing divided by a constant, we know that this is proportional to the numerator, which is the likelihood times the prior. So you can see that now, if we have observed data x, then we can obtain the posterior distribution of theta given x, which is some updated beliefs about the distribution of theta after we have observed the data. So this posterior distribution is still a distribution. Bayesian inference is based on the posterior distribution of theta. However, sometimes we also want to find a point estimate of theta, just like we did for the MLE. So we want to find a single value of theta that can, a single value that is a good estimator for theta. So here are a few options for doing this. The first is the posterior mean, and that is the mean or the theoretical expectation of theta under the posterior distribution. The posterior mean, which we call theta hat EAP, an estimator for theta, is equal to the expectation of theta in the distribution theta given x, so the posterior distribution. It's called EAP, which stands for expected a posteriori estimate. Another possible point estimator is the posterior mode. That is, in the posterior distribution, what value of theta will maximize the posterior probability? So theta hat MAP, which is the posterior mode, is given by the theta value that maximizes f theta given x. And this is called MAP, which stands for maximum a posteriori estimator of theta.